Welcome back. Um, so this is once again the scientific computing course in Lecture 2. We discussed last time a little bit about what programming entailed, and we started doing a little review on C++ because that's the language we'll be using. The idea is that you have some programming experience and that this is either in C or C++ or not, and if it's not, then this is really just meant as an overview of how you do things in C++ versus whatever language you are coming from. So it does mean that if you're not natively a C++ speaker, that the first few weeks are going to be a little bit more work. But that's why the first assignment will be just a pure programming assignment. It's not particularly scientific, just to get everybody sort of on a similar level, to find out if you need extra help. We're always there through email or office hours to help you along and get you used to this language. We're not going to use the most intricate features of the language either. This is not meant as a course in C++. C++ is just a common language used in scientific computing, which competes with Fortran, but is used a little bit more wider than just scientific computing. So that's why we just chose one rather than the other. Slides are combined with these two lectures, lecture 1 and the second lecture. Forward to where we were. We were doing something with functions. I'll put this one up just to remind you, if you're not C++ native, that this is kind of what C++ programs look like. And every C++ program has a main function. Functions are denoted by having a type that it returns. Every function returns a number or a variable, and then its name, and then possibly some arguments. In this case, between the parentheses, there's no argument, so this function does not get any argument. The main function is the first function that's called in a program. So every program can contain a whole bunch of functions. Functions don't do anything by themselves. They're just defined. And when you start a program, one of those functions gets called initially to start the whole thing off, and that function has to be called main. That's the standard according to C and C++, and so that's what you always have. Functions, so functions typically have some arguments. They do something, they return something. They can even not return anything, in which case they're not really functions. The return type, rather than being an integer, could be void, and that's done something that just does something rather than return. So variables. So one thing that's important to realize when we're doing functions and we are passing it arguments, that we really can do this in two kind of ways. And so this is trying to explain the simplest way you could do that. So suppose I have a function called inc that is supposed to increment an integer I. So I pass it an integer I. So in this definition, it says I will expect an integer I, and I will return nothing, void. And then what the function does is just adds 1 to I. So I can call that function from my main function just by defining a variable j equals 10, and then passing that j into the function. And then just to check whether I get the right answer, I return the value of j from the main function. So I can compile this with C++. We're always going to use the C++ 11 standard. So for now, all the compilers will need some sort of flag to tell them that that's what we want. So that's what that is. The output executable will be called passval, and the function, or sorry, the file name is passval.cc. And if I run that, so I just call it with the name of the function, then nothing happens because I didn't print anything, but I did return that value, which in the shell we can get back by echoing $? So it returns 10. Now that's not right, or that's not what you wanted, right? Question? No. Yeah. So what's happening? So what is happening in detail is j is set to 10 initially in this first line, right? That's where main comes in, and is then passed to j. But what happens is that rather than being passed as the variable j, it's actually a copy. So this is a new variable, int I, that just gets assigned the value of j. So int I is a separate variable from int j. And this I variable, yes, it gets incremented by 1, so it will be 11. But this doesn't change the original variable j, because it was a copy. It's a separate variable. Initially has the same value. So we passed it correctly, but we couldn't change it. And that's why this is called pass by value. You just get the value, don't get the actual variable itself. In this case, that's not really what we wanted. So we need another way to do this. And another way to pass a variable is by what's called by reference. The syntax is almost the same. The only thing we've added here is this ampersand, this and sign. And what that changes completely how this variable is passed. It's in this case, if we now compile this, so I've only changed this one ampersand, compilation is the same, and I run it, now the return value is 11. So j is set to 10 again initially, and j is passed to inc, but by reference. And that really means that rather than creating a new variable I really create a new name for the same variable. So j and I are the same thing. It's just within the context of the function, this variable is now called I. It's a reference to another variable. It gets increased, defined by its name. And it does that because in this function, I cannot know that there was some variable j that lives somewhere else, right? So I have to do it that way. It gets increased. Since I and j are the same variable, they're just named differently in a different context, j is also one larger. It's the same data, and then it gets returned properly. It's a nice thing of C++ to be able to do it with just an ampersand. In C, you'd have to do this with pointers. We'll look at pointers later because they have uses, but you don't really need them for passing by reference anymore. Yes. You could implement this differently and have it return the value, and so make it an integer, and then you wouldn't have to pass it by reference. You could pass it by value. Yeah, it would work. Yes. In fact, sometimes you pass by reference even if you don't have to, because if it's really big data type, to make a full copy of that just means that you need twice as much memory. So it can be an optimization to pass by reference, even when sort of semantically you mean a copy. You have to be careful with that, though, because now you can change things. So these are the two kinds of ways, and it's important to know that if you're coming from Fortran, the standard is to pass by reference. So it's good to know that basically how you do it in C++. If you do it in Python, it depends on the context how it's done. Just so you know what you can do in terms of stuff with the variables and the different operators. There's a whole bunch of them. I won't go through them, but the arithmetic makes sort of sense. Logic isn't so strange once you get used to ampersand meaning and. In C, you're also allowed to use sort of verbose logic, saying not and or as keywords. You can assign, you can add, you can subtract, multiply, you increase by 1, decrease by 1. A bunch of operators are. It's a sort of short language in its. So talking about operators, going back to elementary school, what's 1 over 4? Depends on the type. So as written, 1 over 4 is 0. What? 0? That's not right. No, it isn't right mathematically, but it is right programmatically. The thing is, within C++, everything has a type. It's a strongly typed language, and not just variables, also literal expressions have a type. So high between quotation marks has a type. It's actually a pointer to a character string. 0 has a type of an integer. This exponential notation means this is a floating point operation. True is a Boolean. And the reason that this matters is that the operators act differently on different types. So in this case, the types of 1 and 4 are both integers. And the result of an operator acting on 2 integers should be an integer again. So what's the closest integer that looks like 1/4? Well, that happens to be 0. So this is called integer division. You basically have to get the whole part of the answer, and the fractional part is thrown away. So this is a little bit annoying, to be sure, but it is consistent. Whenever you have 2 integers, you divide, you still have an integer, so you know what comes out. If you don't want this behavior, you'll have to change the types. If you want this to be a floating point operation, you'll have to change the types to floating point. And whenever you change types within C++, this is called casting. You're basically casting one type to another type. Here's an example of how you would do that. I put everything in variables, so A is 1, B is 4. C is our integer division, but D is a floating point division, and I've been very explicit here, and I converted both A and B, or their values, into floating point values. Then I take the division and I store that in another floating point. And I print this out, so C is my integer division, D the floating point, and then I also print the integer part of D, just to show you that that's actually what's sort of being done in this case. So the first gives me 0, the second does give me 1/4, and the last gives me 0. So be a little bit careful when you're doing these things, especially if you're hard coding numbers. If A was of type float, all of this would happen automatically, type float. So, but if you're sort of putting literals in, if you mean a float, put a float literal in. And there's a little bit of help, not much, but a little bit of help that you get from the compiler in automated casting. For instance, if you have a mixed expression here, a float dividing by an integer, it casts it to sort of the most powerful or most general type, in which case, in this case, it's floats, so 1/4 is both floats. This can also be done the other way around. So here's a function that's a little bit dangerous. I want to return a variable unchanged. So take an integer, and I return the same integer. Nothing changes. If I pass that variable to, if I pass into that function a variable that isn't an integer, again, I get this automatic type conversion to an integer, and it throws away the 0.3. And so unchanged of 2.3 is 2. So be careful with types and type conversions, because some of these things happen automatically. You have to, these are not details after the fact. You have to know, okay, what goes into my function? Should it be a float? Should it be an integer? And be aware of some of the pitfalls. Okay, so types are strong, but they're also automatically converted, giving surprising results. So that's how we use functions in a nutshell. The other very important thing, especially in scientific computing, are loops. We typically have a lot of things to do in scientific computing, not one thing, and often there's the same kind of thing over and over again, so that's a loop. It might be running over a grid point of grid on a grid, or a set of data points. Doesn't really matter. But the way C++, at least traditionally, sees this is kind of funny. We take, in C++, we take the first element of whatever we want to do, and then we skip to the next element, and we check if it's the last element, and we keep checking that rather than just saying, just go over this whole set of numbers. So it kind of looks like this. These are sort of the two forms of loops. For is meant as a counting loop, and while is a bit easier to understand. While a certain condition is true, you do some statements that hopefully change what the condition does. So while is going until this condition is no longer true, whereas 4 has 3 parts. It has an initialization, a condition, and an increment. The initialization is done first, sort of sets up the loop. The condition is very similar to that in a while. An increment doesn't have to be an increment. It's just something that changes in every loop. So let's look at an example to count from 1 to 10. So here's an initialization of an integer variable I to 1. So initially, I is set to 1. That's the initialization. And here's the condition. I has to be always less or equal than 10. And then every iteration, what I'll do is I'll increase the value of I. So that's the for loop. And then what happens in the loop, what is the body of the loop, is this one statement here. I'm just printing out I. So what happens is I is 1. It checks if I is less or equal than 10. If that's true, it executes a line. And then once it's done that, it does the increment statement. 2, it checks whether the condition is still true. If so, it does it again and again and again. It's very flexible. It's easy to come up with loops where I is increased by 2 every time. It's easy to come up with loops where I is multiplied by 2 every time, because you specify what happens from one iteration to another. So it's general, but it is a bit verbose just for counting to 10. Another thing that I just snuck in here is the fact that this one line is attached to a for loop. Usually, code blocks in C are delimited by curly braces, just as the whole body of the function. But a single line in a for statement can be treated as a block. So this last line is not part of the loop. It's only done at the end. So that's why I only have one line rather than 10 lines of numbers. Very important to keep your indentation proper as well, because if you indented this to be here, your I would tell you that the second statement is part of the loop, even though the compiler would not think so. If you're just starting in C, I would always suggest keep your curly braces everywhere. But you'll see code like this all over the place where there's a single line that is the body of a loop. And so that's what's happening. Yeah? Excellent question. So yes, every function should return its value. But for some reason, and mostly historical, the main function is special, and the standard allows you to not return anything, and will put in the return 0 for you. Only for the main function. So it's not good. It's not good practice. I should have put return 0, but yeah. Now, just because we're doing C++11, I have to mention that there is a third form of loops, which is called a range-based for, which is very neat, but really only works when you're doing somewhat more fancy data types. So the example might be more clearer than just doing the syntax, but I can give it a list, curly braces, for instance, and then say, take all integers I from that list. This is starting to look a little bit more Pythonic, and I'll do the same as the previous one. But the reason we're not going to spend too much time on this is that unless we have a really small literal list like here, we will have to know how to create lists that you can iterate through. And some data types in C++ do that automatically. Others that you might create yourself do not. And so it's sometimes useful, and it's good to know that it exists. But you don't really need it. I just put it in here because we're doing C++11, and it introduced this for this range-based for, which is very nice, but not always the solution. It's also doesn't have the flexibility that we just said. We can't say do this for every other element, whereas skipping an element in the general initialization condition increment form is very easy. So there's less flexibility, but there are contexts where this is just a little bit cleaner. Let's forget about that for now. Just it exists. If you see it, you know what it means. Here's another concept that we will have to deal with to some extent. It's a concept of pointers. And when you're new to so pointers are very simple. There are variables around in our code, and they live somewhere in memory. Memory is basically one linear set of bytes, and so somewhere byte number x is where our variable is. That x is called the address of the variable, so it's where in memory it is. And a pointer is nothing else than an address. Okay, so it's like the difference between your house and the number of your house on the street. They both refer to the house. One tells you where it is, the other is the actual thing. Variables are one thing, the pointers are where the variables live. Okay, so it's addresses of variables. But it's the fact that you can do very funny things with these pointers that makes them so much more complex. If all you needed is the addresses of variables, it's not so bad. So essentially, that's what the memory addresses of the variable. Where is it in memory, rather than the name of this one? And they're also typed. So if I want the address of something that's an integer, it has to be a pointer to an integer. It can't be a pointer to something else. And the type of what you're pointing at is embedded in the type of the pointer. And the notation is such that you'd say type with a star. So type and then star is the pointer to such a type. It can be very useful if you have data structures that need to point to others. You can imagine some sort of graph where one variable points to another variable in some sort of connected way. Linked lists, binary trees are all examples where pointers can be useful. One thing that is both annoying and useful is that you can have a pointer that doesn't point anywhere. So pointers can be variables too. So you can store these addresses in variables. That is your pointer variable. What if they don't? What if they shouldn't point anywhere yet? So you want to initialize them to something that expresses they're not pointing to anything yet. I haven't assigned it to it. So it's just like an empty form. You don't want to not assign it to anything, because then they get some random variable, some random number that happens to point somewhere. So you can tell if you really meant it to point there or whether it was just uninitialized. So there's a thing called a null pointer in C++ that you can just type as null PTR. That shows that this is a pointer that's not going anywhere. Other than the star, the notation of a variable is the same way. So they type star name. Now, name is not a variable of type, but is an address of a variable of type. If you want to find the address of a variable, again, they're using this ampersand. That's the address of operator. So you can take a variable, say an integer, put an ampersand in front. Now you have the pointer to that variable. And then if you want to get something from that address, so say name is now this pointer, then star name gets the content at that memory address. It's called dereferencing the pointer. That's just the name of it. But it gets the content that's at that point in memory. A little contrived example. If you get this, you basically get the pointers. A is 7, B is 5. These are regular integers. Now I'm introducing a pointer variable, so an int star of a pointer. By the way, where you put this star, whether you put it closer to the int or closer to the name, it doesn't really matter as long as you stay away from defining more than one at a time. No, just not doing that, but it doesn't really matter. Liberal with spaces. So int star pointer is to point at A. So it takes A and it finds where it lives in memory and stores that in PTR. So PTR is the name of this variable. I'm assigning a value to 13, so it's no longer 7. And then I'm assigning B another variable, which is the star of pointer. So pointer is the address, star is getting the content from pointer and putting it in B, and then I'm printing this out. So what am I printing out? What should be equal to? There's 3 possibilities. Well, 4 possibilities. 7, 5, 13, or nothing. So who's for 7? Who's for 5? Anybody for 13? Quite a few. Anybody for something else? Okay, so the people that dare to answer were all correct. It's 13. Because I put the value 13 in the variable A, and the pointer was the address of A. So once I take the content from that address, it is the content of A. Now you can do fancy things with pointers, which I would not suggest to do unless you really know what you're doing. Like you could add things to pointers to go to the next address in memory. You could subtract pointers to see how far two variables are away in memory space. Usually you don't want to mess with that too much, but because that's why you get into trouble. The most important bit of thing to remember with pointers is as soon as you have a pointer, assign them either to null pointer or to a variable so that they would point somewhere, because not all of the memory that you can point to is yours. There's memory that belongs to other applications or just writes to variables that are in your application that you didn't want to point to. So as soon as you start writing into that pointer, into that memory, all hell can break loose. If you don't control where your pointers are going, you can get some memory errors that are really, really hard to find.
So coming back to that, imagine we wanted to assign.
Yeah.
Do I need to use the star again?
No. So then it's just pointer. So pointer is it. So it's in a sense easier to understand if the star is here. Right. You see an unstar. The way the parsing works is that it actually sees that star pointer is of type int. Crazy C historics. But yeah, you just use pointer. So you could say pointer equals %b, and now it would point at b. Yeah. So if you do an int star, you would get the address to the variable, and you could also change the variable now because you know where it lives. But every time you want to use that variable, you'd have to write star, say int star x, you'd have to write star x everywhere when you want to use that variable. And which is basically more typing and asking for trouble, because at some point you're going to forget and write x. So ampersand is sort of clearer. The other thing that's good about ampersand is you can't pass a null pointer to ampersand. It has to point to some, well, if you're very clever, you can coax it. But you pass a variable, so it has a memory location that is valid. Whereas with star, you could accidentally pass it 0 or some value that isn't really an address. So it's safer to do ampersand if you just want to pass by reference. If you have an old C function that used pointers and you know it works well, you've tested it, by all means, just use it. But then when you pass in things to that C function, you have to give it the address. So you have to do ampersand everywhere. It's a bit more cumbersome and not really ideal, but it will still work. Okay, so pointers are related to arrays, although that's not entirely obvious at first. An array is a type, but then replicated several times. So suppose I wanted 10 integers, so I just have an integer and integer and integer. There's a notation for that, using so-called automatic arrays, where you define a variable name of type, but then rather than just having that variable, you take square brackets and a number, which is how many of that type you want. Once you want to use one of the, so this is an array of, say, 10 variables, then if you want the first element, you have to say the name of the variable and then, or of the array, and then between square brackets, 0. So the first element is 0. It's a 0-based thing. And the way it's done, and again, this is somewhat historic, but it's still true, is that the name of a variable is equivalent to a pointer to its first element. So I have my 10 elements. They're called, the array is called name. The first variable is, or the variable name is also a pointer to the first variable. So in principle, that's it's not that hard. You can make an array of 6 integers here, 2, 3, 4, 6, 8, 2, and I might want to sum them up. So take another variable that will contain the sum. It starts at 0. I go over all 6 of them, and each time I add to sum a of I. So a goes from 0 up to 5. You see, I don't include the 6 because this is element 5. So this is how C and C++ textbooks will tell you to do arrays. Not that it's no good in a syntactical form, but the trouble is you can't count on this to work. So the syntax is correct, but it might completely bail on you. And the only guarantee that I could find in any sort of standard was the old C standard that says that this will work as long as your variable is not more than 64 kilobytes. I'm sure that when they wrote that standard, that seemed like a lot. It certainly doesn't anymore, and it certainly doesn't in scientific computing. An array of a few gigabytes is not uncommon, and it will fail. So there's a limit that is set to these kind of arrays, these kind of automatic arrays, and it's actually not set by the compiler. It's a combination of the compiler and the operating system. And while you could go and dive into your operating system and try to figure out how you can make it use more memory for your automatic arrays, it's neither practical nor particularly nice, because there's a better way. So this is only bad, really, because you're going to write this piece of code, it works, and now you're going to change your number of elements from 6 to 6 billion, and it just crashes. It doesn't even give you a proper error message. It probably says segmentation fault, and you just have to guess what that means. So we're going to be doing large arrays, and we want to get away from this. And so the way to get away from that is to use what are called dynamically allocated arrays. Here we take the memory allocation in our own hands. And so we use the same idea that the name of an array is also a pointer to the first element, and we turn it around. Rather than creating an array and saying the name is a pointer, we create a pointer. And now we ask for a block of memory using this new construction, so new type and then a number of that type, and assign it to that pointer. Now we know that, so we'll get a pointer to the first element of this array of number elements. Now, since we're doing this by hand and we're allocating memory, when we don't need this memory anymore, we actually have to give it back to the system. If we don't, that memory is gone at least from your application until your application dies. And that's because we have good operating systems now that at least give all of the memory back when your application dies, but still. So you have to do what's called a delete to reclaim or to give back this memory. So new gets the memory, delete releases it. And because it's an array, you have to sort of remind the compiler this is an array with these extra square brackets, nothing in it. So this is good because this will allow you to access all of the memory that is available in your machine. So you have 8 gigabytes in your machine, you can allocate an array of 8 gigabytes. You allocate a second array of 8 gigabytes, you're of course in trouble, but that's to be understood. But it's no longer set by the operating system or the compiler in any sort of way. So you can use the full potential of your system. What's somewhat unfortunate is that this only works for one-dimensional arrays. There's no good multi-dimensional version. So you have a 2x2 array. You're kind of going, well, there's different options you can do, but it's not built into the language. Here's a little example showing that we take 6 integers. So here's our new int6. We assign it to a pointer variable a. So a is the pointer to the first variable. And then we fill it just as if it was a regular array. Unfortunately, with this, we can't use those nice curly braces anymore. But if we have a large array, we don't want to write out by hand in curly braces all of the entries in that. And then the sum is done in exactly the same way. So nothing changed except the initialization and then giving back the memory. But this could, in principle, be changed to work with 6 million numbers. And as long as you have the memory in your machine, it will work. Okay, so we have arrays. They can be dynamic. That's a good thing. We'll do that from now on. There's something tricky, though, to remember when you're passing arrays to functions, and you will, because arrays are the bread and butter of scientific computing. So I'm going to start with something that doesn't use a function, but uses an array, and then transform it into something that uses a function with that array. Here's an array of 10 integers. there's a loop that fills these integers with squares, so the square of 0, 1, 2, 3 until 9. And then there's a second loop that prints them out. I've done something kind of funny in this loop, so I'll have to explain that a bit. Rather than going up to n, here I'm doing this funny size of business. Size of is an old C function or keyword that determines the size of a variable in bytes. Now, the size of b in bytes is going to be n times however big an integer is in bytes. Typically 4 bytes, but you can't count on that. So size of b will tell me how many bytes there are in this array, but I want to know how many elements there are. So if I divide how big it is in bytes, and I divide by how big each of the elements is, I will get how many elements there are. So this is just a different way of doing this. This can be useful sometimes, especially if you don't quite remember what n was, and this isn't as close in the code as it was once. This is a way to determine the size of an array. So if I compile it and have it print this, it'll print the squares up to 81. Okay. So what I want to do now is to say, okay, I don't really like the fact that that the printing and the assignment are in the same function. I want to have a function that always prints an array, and hopefully I can hide all of this cleverness inside the function, and I only have to worry about it once, and it doesn't clutter my code. So here's an attempt at that. I created a function print array, print r, passed it an array, and this is the proper syntax to pass an array. If you don't want to specify exactly how long the array is, so you want to work for all kinds of arrays, you just do square brackets without anything else. And then the same loop is put in here, and we'll print out size of a divided by size of a0. The main function is almost unchanged, except this part of the printing has been replaced by calling print r. So I'm going to compile print r2, and this is the result, 0, 1. That's not good. Nice idea of putting in a function apparently broke. Throw away this code, just stick with this one. Or understand what's going on here, because it would be nice to have a print function. So what's going wrong here is that, unfortunately, this idea that the name of an array is a pointer to its first element is sort of enforced when you call a function, and all that is passed here is the pointer to the first element. So this is actually no different than passing in a pointer. Why did that matter? Because that's fine. I just need to know where this thing starts. It matters because the size of a pointer is very different from the size of an array. So say that integers are 4 bytes, then the size of this array was 40. The size of a pointer in a 64-bit machines, which is most of them now, is 8. So the size of a pointer is 8, whereas the size of the array would have been 40. But I've lost the size of the array. So C++ isn't very good in dealing with arrays naturally. It forgets about their sizes. It just remembers that they're pointers. That's not good. That's annoying. But it's mostly just annoying. Once you know it, the way to solve it is just to pass an extra variable that says how long your array is. So another int n, and then just use that n. Because apart from the size, the pointer acts as if it's an array anyway. The equivalence is still there. I just have to know how long your array. So change the function to include the size. Prints. When I call the print function, again, I have to first say what the size is. And here for this n, I could have used this one because at this point b is an array. So there's this difference between arrays and pointers is annoying, but it's a reality. And so whenever you have a pure C++ array that you pass to a function, you have to pass the size. Now that we've done that, we actually get all our numbers back. Okay, so now there's one thing still kind of bad about this code. It's that I am using automatic arrays, and I just told you that that's bad. So just to not contradict myself, here's a version that uses the dynamic allocation. So new and delete. And other than that, it doesn't change anything. With new, I knew I never had this size. I always had a pointer, so it's almost more consistent to do this. Everything is a pointer. Arrays don't really exist when you're doing it. That way, you don't have surprises and you don't count on the arrays. It's sort of a way of life. Just so you know, there's also a possibility to use new to get just not an array, but one variable that looks like this. You don't really use it much unless you're doing object-oriented programming or if you're doing dynamic data structures. So we won't really see much of this, but it doesn't mean that whenever you do a delete and it's an array, make sure you do put those square braces there. Yeah. In C++, you can without destroying the old array. So you can reassign this. So this pointer here can be reassigned to something that has a different size, but it won't have the content. So you'd have to save the content, or copy it over to your new array, and that's the way you would do it in strict C++ arrays. In C, there is actually a way to change the size, but it's not nearly as nice. And there's other data types that allow you to do that kind of stuff within a standard library, but not with these arrays. This slide should have been earlier. There's an if statement in C++. So if something is true. Now, in principle, you could check if your memory allocation was correct by seeing if it returns a null pointer. In practice, that's not how you do it, but it's just a way to show that an if statement can be done. And much as any statement, it takes a block of code that can be in curly braces or a single line. So if B is the null pointer, it returns 1, which means an error. Otherwise, it does my printing of. So be able to allocate 20 ends. Another thing that I should mention, but that you can live without, is the const type. So you can make a type a constant type, which means that you're not allowed to change it. So it's a good way to get constants, like here. You just put const in front of the whole thing. Const int array size is 1024. Now I'm not allowed to assign anything to array size anymore. So this can be useful as a safeguard for yourself. Okay, this is a parameter, should never change. I don't even want to accidentally change it. Compiler, please make sure that I don't do anything stupid. It can be useful to say that, a variable that you pass as reference doesn't change. So you can say, okay, this is a reference, but don't change this variable inside. So sort of a safe way to pass it, pass in something that you don't want to change. But const is now part of the type, and C++ is very strict about types. And so you'll find when you use const without thinking too much, that the compiler will complain that you're trying to use something that is const where it shouldn't be const, etc. So const in the sense is contagious. Once you start using the const keywords, you're going to have to do it all over the place. Everything has to be so-called const correct. So when you're doing your homework and you want to not use any const, in principle, that's fine by me. There's a good reason to use const. It's a great thing to do. It's good practice. But you know, it's not a trivial thing. It's not just saying, oh, I want this to be constant. It sort of permeates. So use it for constants, like parameters. Use it to say these variables that I pass into my function should not change. Other than that, don't use it unless you know what you're doing. You guys notice that I'm trying to teach you not C++, but C++ Lite. I'm showing you things and I don't use them. This is C++ Lite. This is stuff that you only want to do if you know what to do. Another big topic within C++, and one of the reasons it was created from C, is to do object-oriented programming. We're going to see objects. We're not going to write objects, I think. And the idea of an object is to take together, it's essentially taking data and functions together. So we have functions that we can pass data to as arguments, and we can work on that data and give something back. Sometimes functions are just integrally connected to the data that they're acting on. If you think of them as objects, that might make more sense. So I could have an object called door, and the door can open. Opening anything else but a door doesn't make any sense. So the opening of a door is part of the door. So you can make some sort of semblance of objects where the functions that can act on them are part of it. Yeah, an example would be more clear. So here's an example of an object called a string. So strings in C++ are objects. You define them by including the string header. So now I have the strings at my disposal, and they're called std strings. A lot of these standard libraries live in a namespace that's called std. So you have to prepend it with std : string. And then the name of the string will be s, and it will be initialized by hello. So hello will now go into the string. The string will contain hello, but it will be more than just that string. It will be an object, and so it can do things onto itself. One of the things it can do is it can request its own size. So whenever you have a function that's part of an object, the syntax isn't that you pass that object into the function, but that you say, I have my object s, and then I want the size function inside that object. So s.size gives the size of s. Rather than saying size s, it's s.size. The syntax is a little bit different because size is essentially part of s. So this is the way you could get the length of the string, and it probably should say that it's fine. There's more complicated objects. Here's an object that is a pair of an integer and a float. Shoot, you can pair two things, and then you can get the first and the second element out by using p.first. First is part of p, and p.second. There's a whole bunch of these sort of standard objects, and I won't go through all of them, but string is certainly one of them that you should know about. Pair is of more limited utility. But that's how you use objects. You can write your own classes and objects. So a class is really the type of an object. So S is an object, string is the class. Type versus variable, class versus object. Another syntax thing that you should know about, because you're going to see it, are templates. Now, templates are a really good idea, and I'll show you why. Suppose that I have two functions here, both called squareIt. And in one case, it's squaring an integer, and in the other case, it's squaring a double. I'm allowed in C++ to have functions that have the same name, but do something different, as long as they're distinguished by what kind of arguments they get. So in this case, if I pass a double, it will call this function. If I pass an integer, it will call this function. Overloading, it can be useful. But I still had to write two functions for that to happen. And they are essentially the same, except for the type, right? But I have to do that because C++ is strongly typed. So passing a double and an integer are in principle different functions. So, and you can imagine that I might want to do this for single precision. I might want to do this for other variables, complex numbers, etc. So there's a way to write this once by using a generic function in which we've replaced the type by capital type. And then once you've done that, so to do that, you have to say that this type is going to be a placeholder. That's this template type name. And you just have the code once. Now, if the code is this simple, you say, if this is a 20-line code, it certainly makes sense because you're going to change things. You have to change them in both spots. So the way you call this is use these no brackets. So if you want to make sure you get the double version, you just say squareIt double 3. If you don't, it deduces which of the two you wanted from the argument type. Why is that useful? Because it's mostly useful in classes. They could have complex numbers that are either a single precision or double precision by saying what they are derived from. So derived from two floats or two doubles. You can have a complex int, I guess, vector, different types that are sort of containers that can contain base elements of a derived type. So we'll see that, especially when you're doing complex numbers. This is the way that C++ does it. And because it does it this way, I have to introduce it. So if you're ever going to do complex numbers, you're going to have templates, and they look like this. Finally, libraries, the last bit I'll cover. We've talked a bit about header files, but not too much, and we'll do more next Thursday. Whenever you want to use a header, want to use a library, so functions that you didn't write that are somewhere supplied, you need to include the header file. We've seen a few of these includes already. And then that's just the definition. That doesn't actually say what these functions do, just how they are called. You still have to, in the end of the day, tell the compiler how these things are actually going to be done. And this is in a different library file, which you have to specify at link time. This is a lowercase l. So whenever you compile, at the end of the day, you also have to put -l in the name of all the libraries that are needed for. There's a couple of standard ones that you should look into. String we saw, IOStream we saw. There's input-output, fstream for file input. Containers, which we'll probably discuss to some extent. Math stuff, like square root. And a whole bunch of derived or inherited files from C that are still useful sometimes. So there are a lot of the functionalities in libraries. I think I mentioned that last time too. I talked about namespaces only in the sense that you can have sort of an automatic prefix, and a lot of these things are in standard : So that's just a way of making sure you don't define a variable cout that clashes. Finally, the IOStreams, we saw this one, but we didn't see the file one. I'm just going to show you the file one. So to write to a file, you use an object of type std offstream for output, or ifstream for input, o output I. Give it the file name, and then you can stream these variables into it, these funny operators, in the same way as you would. This is a type, but it should just be std, and you can read them in as well. So this is just it's very simple. It's very similar to writing to the screen or reading from keyboard. You just create this object f in first rather than using c in or c. Yeah. The type of the. Okay, so when you write to a file, basically, and this is a good point, the file doesn't contain any of that information. So this will just print it out. So the streaming operator will see if it's an integer or float and will write it out appropriately. So it says an integer, okay, just print it out this way. Float, okay, I have to do a different format. But the file itself just contains those character strings. There's not a header that says, oh, this is going to be a float, or this is going to be an integer. Although that's something that you might want to do, and in that case, you're going to look at a different file format than just streaming them out like this. So this is the simplest way, but there's better ways to save your data that preserves that information. So for instance, 1.5 here is going to be written as 1 period 5. But if I put something in front of it that says, oh, make it a precision of 10, it's going to write 1.50000000. So you can control your output in that sense. But it still doesn't say that this was originally a single precision floating point. So I can't see from the look of it whether it was single precision, double precision. Maybe it was a complex number that had no imaginary part. Like you can't, or was it an integer? To do that, you'll need different file formats. And we'll talk about file formats at some point, but in a few weeks. Okay. So that's the end of the overview. Really, I suggest dive into the parts that weren't so clear to you. We have an assignment on the website. Let me pull that up. So you'll find it on the right here. It's verbose because I wanted to be very clear what we're doing, but we're essentially creating 3 arrays and writing them to a file. The details you can read yourself. You've got 1 week for them. If you have any questions, email us. Once you're ready, once you've written your code, you can upload it in the assignment Dropbox, for which you don't have to be logged in. But, as I explained last time, if you're late, there's a half-point penalty for every day you're late, so don't be too late. And we really do that so that everybody has submitted all their homework at least a week after, so we can give you the grades back and your feedback. So with all of these, we'll always give you some feedback on what was wrong with the code. We won't just say, it's worth a 6 out of 10. And no, you'll get detailed feedback. And especially initially, that's going to be very important to make sure that, the thing with code and the compiled code is the program either compiles and runs or it doesn't. And if the only criterion in grading was, does your code work and run correctly, almost everybody would get a failing grade because there was something wrong. If we say, okay, this is what you say, you had a hard-coded number and I had to change that, or you're using a slightly non-standard form and the compiler, my compiler doesn't like it and yours did. We can point those out and we can just say, okay, we understand what happened here. Okay, so the feedback is going to be posted right next to your assignments once we're done with it, and so you'll have all of that at your disposal. In the next assignment, you can. Okay, thank you, and see you on